Hermite and Cardinal curves. So one of the splines that people have come up with is this Hermite spline. Basically, it's this spline here where you are able to control both the points it passes and the derivatives at these points. So you control the derivatives at the nodes, and the segments share the endpoints and derivatives. So these are cubics. As we saw in the previous video, with cubics you can have 4 constraints. So it needs to pass this point in the beginning, at this point in the end, and it needs to have this derivative in the beginning and this derivative in the end. And this gives you these kind of handles where you can change the points it passes or change the derivatives, and this will change the shape of this entire spline. Now the constraints themselves would just be like this. At value 0 we will be at control point P0, at value 1 we will be at control point P3, and the derivative at 0 is this control point 1 represented as this vector here, and the derivative at the end of the curve is going to be represented by P2, this vector here. So while this is cool that we can kind of specify where the curve needs to pass and then control the shape of the curve, like how does it curve when it approaches this particular point, it turns out that this can perhaps involve too much manual tweaking. So there is this Catmull-Rom spline where these derivatives are calculated automatically from the points. Now how does this work? It actually takes the previous point and the next point, takes a vector between them, and half of that is going to be this automatic derivative. And what you can see is that you just control the points that the curve passes, or the spline passes if you have multiple segments here. You just control these, and the curvature itself is automatic. So you don't have to worry about the curvature, you just say where does this spline need to pass, and it's gonna create this nice curved spline that passes the points that you specified. Now the constraints, well, at curve 0 it needs to be at P1, at curve 1 it needs to be at P2, and well, in this case we have these other 2 control points here. So when we look at the constraints, we actually have like these 4 points. And if we create a spline, these will be the points that the entire spline passes, except for the very first point on the spline and the very last point on the spline. But when we just look at the one segment in the spline, then we have this point P0, P1, P2. The curve is going between P1 and P2. So the curve at 0 is going to be P1, and the curve at 1 is going to be at point P2. But now these derivatives, these use the other points as well. So the derivative at this starting point of the curve is going to be P2 minus P0 divided by 2. So it's going to be a vector from P0 to P2, and we take half of it. So half of this vector here, this is going to be the derivative at this point. Similarly, in the endpoint, it's going to be P3 minus P1 divided by 2. So we take a vector from P1 to P3, we take half of it, and that is going to be the derivative at the endpoint. And the spline that is constructed in this way is a Catmull-Rom spline. So these Catmull-Roms are actually a specific case of a cardinal spline. So a cardinal spline is exactly the same construction that we had before. So these derivatives are calculated automatically from the previous and next point. But there's also this parameter tension, which is scaling this derivative. So if tension is 1, then we actually have just lines. So it's this piecewise linear spline. But when tension is 0, then we have the Catmull-Rom spline before. And we can kind of interpolate between those two by changing the size of this derivative here. Now from this video you should understand the Hermite spline. So this is a spline where you manually can control the derivatives at the endpoints or not points. The segments share the locations and derivatives. So it's gonna be the C1 spline. We also saw this Catmull-Rom spline where instead of manually controlling the derivatives, these derivatives are calculated automatically from the previous and next point. And we saw that these are a special case of these cardinal splines when tension is 0. We also saw the cardinal splines where there is this tension parameter that is scaling the derivative's magnitude.